Mole review. So the idea of a mole, or the concept of a mole, is really important to chemistry, and we're going to use it a lot second semester. And so it's a concept we definitely want you to have a good handle on as you move out of first semester into second. So in order to do this, we need a couple of things. One, your periodic table, because we're going to need the masses from the periodic table. Also, you're going to need a calculator, and the key thing is it needs to be able to do scientific notation. I know a lot of students use their phone as their calculator. Unless you have a different app, and you could get an app for your phone on this, the typical basic calculator on the phone will not be able to do that. So make sure you have those things before you move on. So let's talk about the idea of a mole first. The reason we need moles is because atoms are so very small that we can't really count them individually. And the reason why we would want to count them individually is because when we start talking about chemical reactions, when we have a chemical reaction, we're going to have like one molecule of this substance reacts with two molecules of that substance to create 5 molecules of something else. So that's why we need to be able to see the actual particles. It's easy to measure the mass of something, we just put it on the scale, but the atoms themselves are what are actually reacting. And so we need a way to relate the the number of atoms to the actual mass. And this is where the mole comes in. So you kind of think of like a mole, like a dozen. It doesn't matter what it is. If you have a mole of something, you always have the same value, just like a dozen. If you have a dozen cookies, you have 12 cookies. If you have a dozen crackers, you have 12 crackers. If you have a dozen chips, you have 12 chips. And now I'm hungry. But anyway, it doesn't matter. And each of these have a different mass. But if I was making something out of them, I would actually like count the number of cookies. And so I need to know how many I have. So we're also going to use dimensional analysis. So a quick review for dimensional analysis. If we were trying to figure out how many cookies, so here's our ending point, are in 6 dozen. So here's where we would start. And the thing about dimensional analysis is sometimes students think it only matters in chemistry. It doesn't. Think about a business. Think about a like hotel trying to figure out how many soap bars of soap to buy for the next year or a certain amount of time. They need to know all sorts of things. They need to know how many people tend to rent rooms in their hotel. They need to know how many rooms are in the hotel. They need to know the time period, take all these things, and then figure out, okay, well, how many bars of soap do I need for this many days, for this many people? Really, what they're doing is dimensional analysis. So again, we have a starting point and ending point, and we also need a relationship. So the units we're working with are cookies and dozen. So I know from the previous slide that 12 cookies is equal to 1 dozen. Oops, I'm hitting the there's a dead spot in the iPad. So I'm just going to rewrite that, not on the dead spot. 12 cookies equal 1 dozen cookies. So I'm going to take these units and they're equivalent to each other. I can use those two things interchangeably. I'm talking about the same amount of stuff. Well, we can put that into a math equation in a certain way and be able to change the units, which is really what dimensional analysis is all about, is starting in one unit and converting it into a different unit. So if I were to start this out, I would always start with the number we give you in the problem, 6 dozen, and you can put it over 1. Then also I think it's a really good technique to then think about where you're ending. I'm ending with cookies. So it gets to be a little bit more visual, and you're saying, okay, dozen are here, cookies there. All these relationships, I have 2 things I could do with it. I can either have 12 cookies over 1 dozen, or I can have 1 dozen over 12 cookies. So mathematically, what I'm doing is I'm multiplying anything by 1. I mean, these 2 things are equivalent to each other. So I can put one of them is going to go in here, and it's going to be the one that makes the most sense. The one that would make the most sense is the one that allows me to cancel out the units and get the units I want in the end. So since I'm starting with dozen here, I'm going to want dozen on the bottom. So I'm going to put this first one I wrote in, so 12 cookies are equivalent to 1 dozen. And what that's going to allow me to do is that's going to allow me to cancel out the dozens, because whenever something's on the top and the bottom, in math, you're able to cancel it out. So I just take the 6 times the 12 and get my answer of 72 cookies. Probably something you do in your head, but really this is what you're doing. You're quickly doing dimensional analysis. We just want you to write it out and be able to use it in other ways. All right, so let's keep going back to this idea of the mole. So if I have 1 mole, the number I have, and it's a number we want you to memorize, 6.02 times 10 to the 23rd atoms. So if I have 1 mole of carbon, that means I have 6.02 times 10 to the 23rd atoms of carbon. If I have 1 mole of silicon, 6.02 times 10 to the 23rd atoms of silicon. Again, it's just like a dozen. 1 mole of nitrogen, 6.02 times 10 to the 23rd atoms of nitrogen. So I could continue this on. Any element, if I have 1 mole of that element, I have that many atoms. And that's really a huge number, 10 to the 23rd. It's hard to even wrap our head around exactly what that means because these atoms are so small. And that makes it such a big number. All right, so let's actually start working on these calculations now. So how many moles, so again, it's always a good idea to figure out where you're ending, contain this many atoms of copper. So here's my starting point. The relationship I need, I'm going between moles and atoms. So I'm actually just going to write out that relationship right away. So moles and atoms, it's always going to be 1 mole. In this case, it's copper. So Cu is equal to 6.02 times 10 to the 23rd atoms of copper. So that is a relationship. It's new. It is something that we want you to work with. So it's like when there was a time before you knew the word dozen, then now you know that dozen is 12. So a few months ago you didn't know what a mole was. Now you need to know that when we talk about a mole, when we're trying to figure out how many atoms are in a mole, the number is 6.02 times 10 to the 23rd. That is just something you need to memorize. So then to start my dimensional analysis, I start with my 6.47 times 10 to the 23rd atoms of carbon. And I'm going to end with some number of moles. Again, dead spot. Moles of copper. I might have said carbon, should be copper. Okay, so again, to figure out these two, the mole and the atom, I can either have it 1 mole of copper over 6.02 times 10 to the 23rd atoms of copper, or I can flip them and have, sorry about that, 1 mole of copper on the bottom, 6.02 times 10 to the 23rd atoms of copper on the top. Again, you'll notice that 6.02 times 10 to the 23rd always goes with the atoms. What goes on the top and the bottom depends on what conversion we're trying to do. So both of these could be right, but again, you have to look at what you're starting with. And since we're starting with atoms, atoms need to be on the bottom because it's always going to be this diagonal, we're always going to see this diagonal pattern. So I put this in, 1 mole of copper is equivalent to 6.02 times 10 to the 23rd atoms of copper. And those atoms will cancel each other out. And then the moles are what I'm left over with, and then I can solve for the moles. All right, so this is where you're going to need to put it into your calculator. So this is where you need scientific notation. So there's a couple things, depending on which calculator you have, there's a couple different ways you can do it. And what you're going to want to do is either talk to your teacher individually, or any calculator you use, there's going to be directions for how to enter in scientific notation somewhere. So you can look at your type of calculator, you can Google it, that in scientific notation, and I'm sure that there is a video on how to enter it in. So a lot of people are like, oh, I just use the caret and the times 10 raised to a power. I will tell you that the sooner you can figure out how to actually do it, so the calculator understands its scientific notation with the shortcuts, the better you're going to be. So what I'm going to do is I'm going to type in 6.47 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. And the reason I'm dividing is because this is on the bottom. So if I brought this all together, I would have 6.47 times 10 to the 23rd atoms over 6.02 times 10 to the 23rd atoms. So that is why I'm putting into my calculator as a division. When I get my answer, I do need to think about sig figs. So I've got 3 sig figs in each of my numbers. So I need 3 sig figs in my answer for 1.07 moles of copper. All right, so the next one, the best thing you can do right now for yourself is try this one on your own. And then start the video up again to check your answer. So go ahead, pause the video, do the work, and then bring it back up. So here is the solution. Again, if you're trying to do this without all these little steps in here, without writing out what the relationship is, without starting here and recognizing that you need to end in atoms, you're not helping yourself. Once students write all those pieces out, then things fall into place. And so that's what I can't emphasize enough is you need to do all the little steps, and eventually you'll get to the point that you don't need to do them, but you have to start out by doing them. So my answer is 2.8 times 10 to the 24th atoms of strontium. Again, you notice I've got moles here, which is why moles are on the bottom, because those will always cancel out. We always have this, whatever's in the top needs to go on the bottom in order for it to cancel out. Because if you think about it, if I put it all together, and I haven't really done this, oh wait, I have a whole bunch of new colors. Yeah, I like this color. All right, so what I do is I have 4.7 moles of strontium times 6.02 times 10 to the 23rd atoms of strontium, and that is over 1 mole of strontium. All right, so you can see how I can just cancel these moles of strontium out, and they're out of there, and then I'm left with this 4.7 times 10 times 6.02 times 10 to the 23rd. All right, let's go on to the next one. All right, so now let's get into grams. So we know that 1 mole of any substance is 6.02 times 10 to the 23rd atoms. Well, what this image is this is 1 mole of 8 different compounds. So there's 6.02 times 10 to the 23rd atoms of each of those elements in that picture. So if we look at carbon, you'll notice this number, this 12.0 grams of carbon, that is 1 mole of carbon. If you look at the periodic table, you might notice that is where that number comes from. In the periodic table, we have 12.01 atomic mass units is equal to 1 atom of carbon. And so what we're able to do is we're able to scale this up. So we can't work at a scale that is only talking about 1 atom, so we have to scale everything up. And so that's where we get the relationship between grams and moles from the periodic table. So what we're looking for on the periodic table, we're always going to use the average atomic mass, because again, we can't guarantee that we only have 1 isotope, so we just have to use this average atomic mass for any of the elements. So if I had 1 mole of potassium, I could say that 1 mole of potassium is 39.10 grams of potassium. So that's how we use that relationship from the periodic table. Every element is going to have a different mass. So let's start again with dimensional analysis with these conversions. So I'm starting with grams of titanium. That's my start. I'm ending with moles. So grams to moles, whenever you see grams or you see the word mass, you're going to need the periodic table. So we have to find titanium on the periodic table. Titanium is element number 22. So I can say that 1 mole of titanium, and I find the average atomic mass on the periodic table, which is 47.88 grams of titanium. So that's my relationship between those two things. So I set up my dimensional analysis, 54.27 grams of titanium. And I'm going to end in moles. Again, this, I can use that. I can put 1 mole on the top. I can put 1 mole on the bottom. The way I decide that is really, or it is always the unit I'm starting with. Since I'm starting with grams, grams has to go on the bottom. So I've got 47.88 grams of titanium on the bottom, 1 mole of titanium on the top. So then I do my calculation. I take 54.27 divided by 47.88, and then I'm rounding it for 4 sig figs for 1.133 moles of titanium. So again, what I did, I figured out where I was starting and where I was ending, and I also figured out the relationship between the two things. So now from dealing with grams or mass and moles, I get the relationship from, this is from the periodic table. Okay, so again, best thing to do on this next one is to try it on your own. But again, do those steps. So one of the things you definitely, want to do is identify start and end, and then write the relationship. Again, eventually you won't have to do this. Right now, until everything falls into place, and this is one of those things that eventually, for students, if you keep working, it clicks in. You're like, oh, that's easy. Why didn't I get that before? But it takes different amount of time to get there. You have to be willing to stay with it, and eventually you can get there. So you write the relationship, and then you set up the dimensional analysis. All right, so go ahead and do that, and then, or stop the video, do that, and then start it up again when you're ready to go. And here we go. So I'm starting with moles, and then the reason I have to have moles in the bottom, because you might notice if you just looked at the old one and you put the grams and the moles in the same spot, you're missing the point. You're missing the idea that whatever unit you start with here needs to be the same unit down there. That's the only way that they're going to cancel out. So that is where you start first. Whatever unit you're starting with, that is the same unit that goes on the bottom. And then since they're both on the top, I'm multiplying these across to get the 13.6 grams. All right, so now we want to bring these together. There's no new relationships, all right? You have two relationships you need to be familiar with. One is that 1 mole of whatever it is equal to 6.02 times 10 to the 23rd atoms. The second relationship is that 1 mole is equal to some number in grams, and this number comes from the periodic table. That's it. Those are the only two things you might use. You're not going to have to come up with something else. These are the two relationships that you're going to need to use in order to do all these calculations. Sometimes you just need one of them. Sometimes you need both of them. So if we're going to go between atoms and grams, we're going to need both of them. There's no new relationship that goes from atoms to grams. You can kind of think of moles as the only doorway that allows you to get from one to the other. So again, but our process is going to stay the same. So we identify, okay, we're ending here. And sometimes in problems, this also could say mass. If it says, what's the mass? We're going for grams. You can just assume that. Here's my starting point. All right, so then I can identify my relationships. Well, I see the word atoms, so I know I'm going to need the relationship that involves atoms. 1 mole is 6.02 times 10 to the 23rd atoms. If you don't see the word atoms in either the beginning or the end, you're not going to need that relationship. Let me say that again. If you don't see the word atoms in the problem, you are not going to need that number. But I do see the word atoms, so I know I need that. So I see the word grams or mass, so now I also know I need the mass from the periodic table. We're talking about germanium, so 1 mole of germanium, which is Ge. It's over there on the right side, element number 32. The number of grams, 72.1 grams of germanium. All right, so I have my pieces. That should, again, dead spot, that should say geranium. Or germanium. Geranium's a plant. Okay, so now I have my pieces. Now I need to put them into place. So I'm starting with the atoms. 1.26 times 10 to the 23rd atoms of germanium. All right, and I'm going to end with some sort of grams. Okay, so I need to think about the pieces. So if I'm starting with atoms, you have to think about, okay, well, whatever we start with, that needs to go on the bottom. So I'm going to have atoms on the bottom so they can cancel each other out. Well, the only thing I have that I can put opposite of atoms is moles, because that's the relationship. So then I'll have moles. Then, again, I'm trying to get over here to grams. So I'm going to have to put moles on the bottom, put grams on the top. So those are going to cancel out, and then I get the grams. So putting them in any other order doesn't make sense, because I am trying to do this very logically. Whatever unit I start with, I get rid of that unit, move into what it's equal to. And then I get rid of that unit and move into what it's equal to. So when I take that and put the actual numbers in, 6.02 times 10 to the 23rd atoms of germanium, 1 mole of germanium, that's going to allow those to cancel out. Then I use the other relationship, 1 mole of germanium, 72.61 grams of germanium, so they end in grams. The other way you can look at it, some students find it easier to think about, okay, where am I ending? So that needs to be the last place I go. So they sometimes fill in that second to last one and then work their way backwards. But it's really important to recognize where you're ending with this so that you can cross everything out. So these moles would cancel out here. And now when I put it in, I have multiple things to do. I have to take the 1.26 times 10 to the 23rd, and I have to divide it by 6.02 times 10 to the 23rd. And then that answer, I have to multiply by 72.61. Again, if you're using it as scientific notation in a calculator, you don't need to worry about any of the parentheses. The calculator will just do exactly what you want it to do. If you are using, like, you're still typing in times 10 raised to a power, you have to be really careful with parentheses, which is why I really think that you should learn how to enter it into scientific notation in your calculator. So with sig figs, because I can only have 3 sig figs in my answer, I get 15.2 grams of germanium. All right, on to the last example. Again, the best thing you can do is to stop the video, take your time, do all the steps. Remember, first step is going to be ID, start and end. It's a little and symbol. Second one, write the relationships. Again, you only have 2 possible relationships. Look at the units you're starting and ending with and see which ones you need. Moles in both of them. So, but in this case, we see atoms here. So I need the relationship that has atoms. And I see grams. So I need the relationship that has grams. Third, set up your dimensional analysis. All right, so you can go ahead and pause and then do that and then pick the video back up. And here's your solution. Again, make sure you have the relationships written out. I know I need the atoms one because it says I'm ending in atoms, and I know I need the grams because I'm starting in grams. That also is going to tell me where I need to put them. Because I'm ending with atoms, that's going to be the second one I need. Starting in grams, that's going to be the first one I have to deal with. So that hopefully helps you. Make sure you're doing some more practice problems with this, and then let us know when you want to reassess it.